All right. That kind of day. End of a semester blues. Yes, they applied to faculty as well as students. Okay. So, well, this is the last new material. So what we've seen up to this point is several numerical integration techniques. We've seen Newton-Cotes rules, which are a foundation for better categories of techniques, composite rules, and then also Romberg integration, which is a combination of composite trapezoidal rule plus Richardson extrapolation to get higher order accuracy. But we have one technique left for today, and that is, well, my favorite and many people's favorite who have to deal with these kind of techniques, Gauss Quadrature, and that's designed to maximize the degree of accuracy. Now, one thing that's come up in the quizzes, since I've been grading a lot of Chapter 8 quizzes, now the degree of accuracy, that is the highest degree of polynomial that is guaranteed to be integrated exactly by whatever quadrature we're using. For example, Simpson's rule has degree 3. You give it anything, any cubic or less polynomial, the approximate integral will actually be exact. As opposed to, so it's not the same as order of accuracy, which is the power of h for composite rules. So for example, Simpson's rule, composite Simpson's rule is fourth order accurate. Composite trapezoidal rule, second order accurate. So order of accuracy means the same thing here as it does for differentiation rules. The error in all of those formulas had a power of h in it. So, and the thing is, depending on how you're building your composite rule, you can really have rules of any order of accuracy. The examples I presented happen to be like 2 second-order ones and 1 fourth-order one. But if you use a composite rule that's based on a higher degree, like Newton-Cotes rule, then you could get higher-order accuracy at least up to a point. Like if a degree is too high, then you might get negative weights. So there's some confusion about these terms. So degree of accuracy is about integrate polynomials exactly. Order of accuracy is about the power of h. So keep that in mind for the quizzes. And of course, as a reminder, you can submit if you get a quiz graded back to you and you lost some points, you can try again. I know some of you do try that, but not everybody. Where we're going? Well, that's easy to answer today. We've hit the end of a line for a semester. There's no time left. Okay, so now the actually one thing I want to check, make sure I did this. Okay, on the site where I put the practice final. Okay, so there should be 8 problems in here. Okay, yep. All right, so these 8 problems are representative of the kind of regular problems you will see on the real thing. And so that will be, so these problems, 8 problems, will be worth 6 points each for a total of 48. And then there will be 26 lightning round questions worth 2 points each. So the grand total of everything is 100, as always. The questions from like a concept check from homeworks 2, 3, and 4, so chapters 2, 6, and 8, are your best preparation for lightning round questions. There will be differences, but if you're able to understand what's going on in those questions, then you'll be in good shape for this. Does anyone have any questions about a final, homework, anything? Yes?
Just if we're thinking about doing the oral final,
yeah.
do we come to class Thursday, or since we're doing
no, you were absolved from coming to class on Thursday. So I won't be taking attendance on that day either. So if you don't show up, then I'll assume that's what you're doing, because otherwise your grade's kind of blown up. But okay, because the way it works, we have 75 minutes of class, so I'll spend the first 35 minutes doing review. Has anyone dug into the practice problems yet? Anybody? You're also quiet. Take it as no. Okay, we might want to soon, because that's what we can talk about during the first part of Thursday. Or you can email me about it in the meantime, or even and then during the final 40 minutes, so Teresa will be up here to hand the exam out to you guys, and then I will be down there handing it out to whoever is there to take it, of the 3 students who are enrolled, and then I will I'll mark everything up right away, and then on Tuesday we'll resume. So okay, any other questions? Yes.
So the exam does cover everything that you've done. What kind of questions?
Yeah, it is comprehensive. Yeah.
What kind of questions?
Oh, okay.
Will it be similar to the written file?
It's the focus is going to be more like the lightning round kind of questions, more in a conceptual. Like, for instance, I'm not going to ask you during an oral exam to go to the board and generate a whole divided difference table and then write out some interpolating polynomial like you've just done on homework 3. I may ask you questions related to that process, like certain tidbits of it, but the time frame doesn't really permit having you work through those kinds of problems from end to end. So that's one key difference between this and like what's on the written final. But for example, for something like that, I could ask, like say if you're doing oscillatory interpolation, how do you fill out a divided difference table when you have points listed that are the same? How do you handle that? What if it's 2 points that are the same, or 3 or 4, or like if I give you a divided difference table, how do you make the polynomial from there? Things like that. Also, my favorite kind of questions for oral are things like, what's an advantage of Newton interpolation over Lagrange? Why would we use Gauss Quadrature instead of Newton Cotes? I like to compare methods, things like that. Okay. I think so far I've only had 2 people commit to the oral, but of course you still have time to think about it. Okay. Other questions? Yes. Oh, we figured out a time. Yeah. So because I'm going to be around, available most of the time during finals week. Let's see, or even actually, I've given the option before of taking it during finals week. No, sorry, during this week to take some of the load off finals week, and I've just realized that a really great day. Well, but except Thursday doesn't work because I'm down at the coast, and then Wednesday I'm going to be up in Vicksburg. But Friday is a fantastic day for that because I have practically nothing on my schedule all day long. So I think I have something at 11, and that's it. So if you want to get it out of the way early, that's an option too. Let's see, during finals week, well, okay, so I'm giving a written exam Tuesday at 4:15, so that's out. But yeah, Monday is mostly blank. And then yeah, the rest of Tuesday, all of Wednesday, I don't have anything on the schedule. I have a couple things on Thursday. That Thursday's less free, but I can make it work. So, but the thing is, I want to. I mean, you guys all have different final schedules, so I'm trying to work with that. So definitely not a stupid question. Anything else? Yes.
You said the written exam won't be like writing code on paper, right? It'll be more.
That's right.
Okay.
Yeah. Well, the thing is, I may provide a code snippet and ask a question about it. That's the extent of it. Yeah, it's because certainly for the regular problems, what you see in practice, that's the kind of thing. Like I'd be like changing the particulars, like what functions involved. Yeah. Okay. You know, I imagine, and I'm guessing you would agree that when it comes to the coding part, you guys have suffered enough. So, anything more? Okay. All right. Now, okay, so for our very last topic, Gauss Quadrature. Okay. So, for the techniques seen so far, so we have, and really I'm going to give a quick rundown of why they're not so great. I mean, they all have their advantages and disadvantages, but since I'm introducing a new one, I want to focus on the disadvantages. So, like Newton-Cotes, you can't use many nodes. You get negative weights. Runge's example is a perfect example of that. And then we have composite rules. So they are one way to offset, to work around a drawback in Newton-Cotes rules. But the thing is, can still require zillion nodes. Computationally expensive. And one of my favorite examples of that, I've mentioned this before, but we're putting down in writing here. This integral for a Gaussian function requires, let's see, 2,500 nodes. Those are and by nodes, those are the x values for 8 digits of accuracy with the composite trapezoidal rule. And then much better, like around like 35 nodes for composite Simpsons. So you already see the fourth order accuracy of composite Simpsons compared to the second order accuracy of composite trapezoidal leads to a big gain there. Now, 35 nodes does not, it doesn't sound bad, especially in contrast to 2,500. But I want to point out. We can still do far better than even that. Okay, so we're looking at a different approach, and so the goal of Gauss Quadrature, and I found that many people refer to it as Gaussian Quadrature. Either name is fine. Okay, is to maximize the degree of the quadrature rules. In other words, we want to be able to integrate polynomials to as high a degree as possible with however many nodes we have. Okay, now, so what we could do is, in any given quadrature rule, quadrature, how much flexibility do we have? Okay. Actually, go into a new page of this. Okay. So we have, because we are free to choose n nodes and weights. So if I want to describe these nodes, so this quadrature rule, by choosing these n nodes and n weights to maximum advantage, what I can do is I could say we can require the following: that the integrals of polynomials of up to a certain degree are exact. So I can say, like, x to the 0 must be equal to I equals 1 to n. My nodes raised to the 0 power times my weights. So the idea is what's on the left side is the true integral, and what's on the right side is the quadrature rule. So we can require that the integral of x to the I, or I should say, to be handled exactly. So I could start with this, degree 0, and then I can just keep going up to degree 1. Okay. And so on. So, and of course, we know what these are supposed to be. We can just work those out. And then we can set up a system of equations. So the idea is I can, whoops, I didn't realize I had pasted this as many times as I had. So let me fix that. So x0, x to the 0, x to the 1, 2, 3, and we have the same thing on the right side. That should be xi cubed. Okay. All right. So in other words, what I can do is I can try setting up a system of equations. So it's a system of 2n equations, and then we have 2n unknowns. Those unknowns would be n nodes, whoops, the x's, and then the n weights. Okay. All right. So I can set up as many of these equations as I can until I've used up all my flexibility, because in order to make sure I have a chance of a unique solution, I should have the same number of unknowns as equations. So the number of equations and unknowns should be the same. So with that in mind, what is the maximum possible degree that I could possibly hope for? Keep in mind how this started. I said as many equations like this as I can, given the number of unknowns that I have. Yeah, 2n minus 1. Okay. So one approach to Gauss Quadrature is direct construction. And what I mean by direct construction is solve the system of equations. So I'm going to write out what the system of equations is for a particular case. Let's say my interval AB is minus 1 to 1. And let's let n equal to 2. So I have 2 nodes, 2 weights. So I have 4 unknowns altogether. So I can have this system of equations, 4 equations. So I'll have, for instance, x1 to the 0 times w1 plus x2 to the 0, w2. And that must equal the integral from minus 1 to 1 of x to the 0. And that is, it's the integral of that is 2. Okay. And then if I just go ahead, if I keep going, so I have 4 equations with these increasing powers. Okay. 1, 2, 3, and then 1, 2, 3. And then the integral of x squared. Okay, well, okay, I'll fill these in too. X to the first, x squared, x cubed. Okay, now let's see how well you remember your Calc 2. X to the first, x cubed, the odd ones. Can anyone tell me what those are equal to without actually doing any work? Why? Odd function. The integral of the odd function over a symmetric interval is 0. For x squared, you can't say it's 0, but it's equal to twice the integral from 0 to 1. So the integral of x squared from 0 to 1 is 1/3, so you double it and you get 2/3. So this is your system of equations to solve. Now, here's the problem, though. You might think, okay, you go ahead and solve this. And actually, for this particular system of equations, you can. Like one variable you can eliminate right off the bat, because I can say, because anything to the 0, of course, is 1. So I can just say w1 plus w2 is equal to 2. So that lets me eliminate one of these weights from the other equations. Now we're down to 3 unknowns. But this kind of a system of equations is very difficult to solve because it's nonlinear. Notice we have all the x's. These are unknowns now. In interpolation, they were given, but now they're not. They're unknown, and because of raised to powers, you can't just do Gaussian elimination. Those kind of methods for solving linear systems that you learned in 326. That won't help you here. Now, I think I might have given it as a homework problem. I don't recall if I assigned it. To actually work this out for the n equals 2 case. So that one's not so bad. But if anything beyond that, no. So we're not going to do that. So we need a different approach. Okay. Now, so for this, we need so I can actually show a way to get these nodes, but it turns out that the question of what the weight should be is easier to resolve because Gauss Quadrature rules they are interpolatory. So what that means is, well, can anyone tell me, because this came up on a quiz, for an interpolatory rule, once you know what the nodes are, how do you get the weights? It has to do with interpolation, but yes, the weights are the integrals of the Legendre polynomials for the nodes. So really, this is about getting the nodes. Once we know the nodes, the weights will follow. So at least we know how to do that. Okay. Now, for the so how are we going to get the nodes? So this is going to be kind of weird. So I'm going to we're dealing with generic integral. And I'm going to assume that f is a polynomial of degree at most 2n minus 1. All right, so it's a kind of polynomial that we ought to be able to integrate exactly. Okay. So our quadrature approximation has this form using a generic quadrature rule, f of xi times the weights plus some error. Now, but the thing is, because we're assuming that our quadrature rule is interpolatory, what we can say is our quadrature rule is equal to the exact integral of a polynomial of degree n minus 1. Where this polynomial, p n minus 1, interpolates f at the nodes. Okay. All right. So this gives us a handle on what the error looks like. So the error is just the integral of a difference, because here's the integral of f. This, from the equation below, is the integral of p n minus 1. So I just move this to the other side, and now we have our error. Now, I'm going to let en, or en minus 1 of x, no, let's call it e of x, equal the difference. Okay, so actually I can go back up here and say that the error is the integral of e of x. Okay, so I'll just do it this way. All right. Now, f is a polynomial degree 2n minus 1. Pn minus 1 is a polynomial degree n minus 1. So we go ahead and subtract them. Therefore, this polynomial is a polynomial also. And we take the maximum degree involved, 2n minus 1. Okay. Now, these points, these two polynomials, Pn minus 1 and f, they agree at the nodes. So what that means is this error polynomial has those nodes as roots. Now, when a polynomial has certain roots, well, what can we do? That means we can factor them out. So I can say that e of x is I have the part of a factorization as these n roots okay, Now, this polynomial has degree n2n minus 1. We have n factors here, and then we have something left over. I'm going to call it r of x. Although I want to include the degree. So, based on the degrees of everything that I put up here, this is a polynomial. What I'm factoring out is a polynomial of lesser degree. Then we have this polynomial, r of x. What is its degree? I think someone might have said it very softly. Bless you. All right. Degree 2n minus 1. This is factored out. You can see how many there are. So what's left? What? I'm sorry, I couldn't hear. What? N minus 1. Yeah, because n plus n minus 1 is 2n minus 1. Every time you factor something out, that subtracts from the degree. Okay. I really should say at most n minus 1, but okay. Just because we have this partial factorization here. Okay. So now we can say that the error is equal to the integral of these linear factors times r minus 1 of x dx. Okay. Now, what I want to do is find these nodes, x1, x2 up to xn, that I've not yet chosen, so that this whole thing, this integral, will turn out to be 0. And for that, I need to step back to a concept that you saw in, you would have seen in Cal 3. And I know you're probably going to be hard-pressed to recall this unless you've just recently taken Cal 3. What does it mean for two vectors to be orthogonal? So if you can recover the dust off your Cal 3 hat and put it on. Yes, the dot product is equals 0. Okay, now let's push this a little further. The dot product, if I have two vectors, I'll write the dot product this way. So you remember how a dot product is computed from two vectors. What do you do? Yes, you multiply corresponding components and you add them up. Okay, now, to address a question of, it might be on your minds, is why on earth am I talking about this now? I'm going to generalize an inner product of two functions is defined to be the integral of their product. Now, the reason why this is a generalization of a dot product is I will recall for you the definition of a Riemann integral. Where you take your integrand, evaluate it at several points, and then you multiply it by a delta x. Okay, so you could think of this as taking this sum of products to the extreme, where we're evaluating f and g at infinitely many points, multiplying. If you think of f and g as not being functions, but infinitely long vectors, you are multiplying corresponding components, f of xi, g of xi, and then you're literally adding them all up. So you can see a relationship between the inner product of functions and a dot product of ordinary vectors in a n-dimensional vector space. So we say that functions f of x and g of x are orthogonal if their inner product is 0. So same notion of orthogonality. It's just the way we are taking this kind of a product is modified to be appropriate for the situation. Now, it has to be specified what the interval AB is, because if I change the interval, that changes the inner product. So two functions that are orthogonal on one interval AB are likely not going to be orthogonal on another. Okay. So what we can do is, so the way Gaussian quadrature works is that the nodes are the roots of a polynomial of degree n that is orthogonal to all polynomials of lesser degree. Because what happens is, if I go back to this error up here, I'll repeat it down here. The error, I can introduce some notation here. If I define this polynomial, pi n of x, to be the product of its linear factors, okay, just for a shorthand, then the error in our Gauss Quadrature rule is equal to, well, that's already known to be the integral of those linear factors times Rn minus 1. But that is the inner product of this polynomial, pi n, with this polynomial, Rn minus 1. Now, Rn minus 1 has lesser degree. It's degree at most n minus 1. This is degree n. Therefore, the error is 0. Therefore, the integral is exact. Okay. All right. So, here's the main point about Gauss Quadrature and how these rules are obtained. We find a polynomial. We decide how many nodes we want. So that's n. Then we obtain a polynomial degree n that's orthogonal to all polynomials of lesser degree. Once we have that, we take its roots. Those are the nodes. Once we have, so actually, I'll put this down for procedure. Oops, that's totally spelled wrong. Okay. All right. So choose n, the number of nodes you want. And then I'm going to add another step here. Find okay, actually, Gauss Quadrature rule, I'll be more specific, on an interval AB. All right, so that has to be known. Okay. So then I'm going to let this polynomial, Ln of x, be the nth degree Legendre polynomial. I'll talk more about those in a second. But the reason why we need them, okay, actually, I'm going to put this onto a new page. All right. So these polynomials, the Legendre polynomials, these are orthogonal polynomials on the interval -1 to 1. So then we get the roots of ln, and those would be the Gauss Quadrature nodes, at least on -1 to 1. And then the integrals of the Lagrange polynomials. Now, Legendre, Lagrange. They both start with L. They both have G and N in them. They are totally different. That's what I'll head that off right now. And we've seen Lagrange polynomials before. You know what those are. Okay, so the integrals of Lagrange polynomials for these nodes that we have. Okay, so these roots are referred to as. Stop that. God, I hate this thing sometimes. I know I say that every class. Shut up. Okay. Okay. So the integrals of the Lagrange polynomials corresponding to these nodes are the weights, at least for -1 to 1. Now, can anyone think, if we have the nodes and weights for -1 to 1, but we actually want the nodes and weights for AB, what would be the fairly straightforward way of getting them? Yeah, you scale and shift. So what you do is you scale and shift the nodes to AB. All right, so that would be, okay, so I don't recall what notation I used in the book. I don't feel like looking. So tilde I will be the nodes for AB. So all we need to do is we multiply the old nodes by b minus a over 2, because -1 to 1 has width 2, so we divide by that width. Then multiply by the width we want, b minus a, and then we have to shift by a plus b over 2. So that's so scaling and shifting is all we need to do for the nodes. And then all we have to do is scale the weights. So that works very similarly. We just multiply the old weights. Actually, I'll do it, put it over here. We just multiply those by b minus a over 2. Okay. All right. And there you have your Gaussian quadrature, your Gauss Quadrature rule. Okay. Now it turns out that for reasonable values of n, steps 2, 3, and 4, you actually don't have to do them, because other people have gone to the trouble of doing this already. So if I look up Gauss Quadrature, I'll make this a little bigger. Okay, but they call it Gaussian, whatever. So here, let's see, make it a little bigger still. Yeah. Shut up. Okay, here, for n equal 1 up to 5, here we have, they've worked out the roots of Legendre polynomials. So here are the nodes. So for instance, for n equal 5, 0 is a node, and then we take plus or minus for both of these, and those give you the other 4 nodes. And here we are to several decimal places. And then here are the weights that go with those nodes. And in the book, I have tables of the nodes up to out to several decimal places. Also on the formula sheet for a final, I have those nodes and weights also. So that part is done for you because it's really a pain to do otherwise. And people have published books that have nodes and weights to 15 decimal places or whatever for larger values of n than this. Because one of the drawbacks of Gauss Quadrature is if you don't have the nodes and weights from -1 to 1 at all, they're really a pain to get. Because finding polynomial roots is something I meant to cover this semester. It'll be covered next semester. Is not really a surefire thing. And I want to say I brought the Legendre polynomials. Okay. All right. So plenty of information about the Legendre polynomials. If any of you ever take Math 415, do you still have to take that, the physics majors? Okay. Oh. I think we haven't offered it lately. Oh, it's the other second differential equations class because there's 415 and there's 417. What? What? Well, yeah. Because 415 would be in the fall, and then 417 would be in the spring. Well, if it makes. So.
We're supposed to take it. We've replaced a lot of our maths because they're not offering them.
Yeah, I don't know why we stopped offering 415 because it's chock full of info, but it was also a really hard class. Okay, so you guys are still taking 417, or you already did, or yeah, right. Oh, okay, so interesting. Okay, so yeah, so well, anyway, these polynomials are covered and other orthogonal polynomials are covered extensively in. Okay, I should say they were covered extensively in 415. So these are the first several Legendre polynomials that have been worked out. So they start out simply enough, 1 and then x, and then they increase in degree from there. And notice the even degree ones have only even degree terms, like 4, 2, and 0. The odd degree ones have only odd degree terms. So these Legendre polynomials are orthogonal polynomials for the interval -1 to 1. But by contrast, so there are several families of orthogonal polynomials that are orthogonal on different intervals with respect to different weight functions. So what I mean by a weight function is that the inner product that's involved that defines orthogonality is, so you have f of x, g of x, and then you have a third function in here, w of x. That's the weight function. So once you have a, b determined and then w determined, that describes your inner product. That describes in what sense you're saying polynomials are orthogonal. So examples, so Legendre polynomials. Okay. Whoops. Okay. So Legendre polynomials on -1 to 1. And the weight function is just 1. So it doesn't really appear. We also have a Chebyshev polynomials. Those are orthogonal also. On the same interval, -1 to 1. But the weight function is 1 over the square root of 1 minus x squared. Which is kind of weird because this function is actually undefined at x equal plus or minus 1. So it's undefined at the endpoints, but it's well defined in the interior, so that's okay. Okay, and then if I were to look up orthogonal polynomials, but I could probably link to it from here. Okay, yep. Yep. Sorry, not giving to Wikipedia now. Okay, maybe later. I think somewhere, but probably a list. I thought they would have one. Oh, okay, yeah. Jacobi polynomials, Legendre, Hermite, etc. This is not the same as Hermite interpolation. Yeah, Chebyshev, Legendre. So many well-known families of orthogonal polynomials here. All, like for instance, the Legendre polynomials are orthogonal on 0 to infinity. So I'll add that to the list. So 0 to infinity. And the weight function is e to the minus x. Because a polynomial would normally not be integrable on 0 to infinity because it goes off to infinity. You're not going to have a finite area under a curve. But if you multiply it by e to the minus x, it's going to 0 more rapidly than that integral is well defined. Okay, so you'd have to work with a different weight function and get that Gauss Quadrature rule fresh. But once you have that, then you can scale and shift to any other interval if it with a compatible weight function. So, but this procedure here, like this part, steps 5 and 6, is what you're dealing with, for instance, on a problem on a test, where you're given an integral to evaluate to approximate using Gaussian quadrature. Then you can look up the nodes up in a table and scale and shift them, just because orthogonal polynomials are among my favorite subjects because they have so many applications and things work out so beautifully with them. But unfortunately, time doesn't permit to really get into them like that, at least not in this class. You can always take Math 772, I guess. So now, a very important property or properties of Gauss Quadrature. I hate how the screen goes blank like that. Okay. So first, already touched upon, a high degree of accuracy compared to other rules. So for instance, a Newton-Cotes rule with n nodes has degree of accuracy at most n. But a Gauss Quadrature rule is degree 2n minus 1, almost twice a degree. So they're much more accurate. Also, they're guaranteed to have positive weights. No matter how big n is. So that's where Newton-Cotes rules break down. The nodes are much easier to get. You have these equally spaced nodes. It's very convenient. But once n gets to even a modestly, still not even a large number, n equal 11, or actually even earlier than that, you will definitely have a negative weight from that point on. But I went to a talk where people were computing literally millions of Gauss Quadrature nodes. I'm not sure why one would want to do that, but they did. But no matter how many, you're always going to have positive weights. So, and that's very important. So that guarantees that as n goes to infinity, the approximate integral converges to the exact integral. So that's something you don't have with Newton-Cotes rules. That it won't converge because of the negative weights. So now composite rules do too, but generally you don't need many nodes of the Gauss Quadrature rule. So returning to this integral I showed earlier of a Gaussian function that cannot be done analytically. You can get 8 digits of accuracy with only 5 Gauss Quadrature nodes, compared to 30-something with Simpson's or 2,500 or so with trapezoidal. So it really is now, again, not always. Like I've said it before, there's no clear winner when it comes to numerical integration methods, but most of the time, Gaussian really is the best. And because in terms of accuracy and robustness, having a reliable answer, they're very hard to beat. And that helps with efficiency. If you don't need many nodes, then your rule is more efficient to evaluate. Now, granted, the nodes can be hard to get if you don't already have them in a table. In most typical applications, chances are there would be nodes available, not just for Legendre polynomials, but even for other families like Legendre polynomials that for which these are not useful. And that's why a lot of numerical integration software is based on Gaussian rules for this reason. So so except for certain special cases, they're not like periodic functions that use composite trapezoidal. Gaussian would be the best choice. Okay, so well, that's the last topic. And there's only 5 minutes left anyway. So are there any questions about anything? All right, so be sure to look at the practice test. Bring your questions on Thursday. I'll be doing it from a coast, but so have questions ready to shout down southward for those of you who are in the same room with me now. I put out all the quizzes. They're all posted in Canvas, so you can get those out of the way. And be sure to get cracking on homework 4 because you have until December 8th to get all done. So if you are thinking about the final, even if you're not sure, it's a good idea to let me know, because then I can sort of keep that in mind. Like having even approximate head count or upper bound is helpful, just so I can accommodate everybody. All right. Yes.
Just double check. So Thursday, part of the test that we'll get is the problems and the.
No, you're going to see everything.
Oh, we're going to see everything?
Yes.
Okay.
I'm going to regret that, aren't I? Yeah, I thought about partial. I mean, I might have done that last time.
Yeah, last time.
Yeah.
That's what you did.
Yeah, I didn't want to keep track of that many files, so yeah. Okay. I'm glad that meets with your approval. Yes.
So, if we still come Thursday and look at the question and afterwards decide if we want to do the oral.
Okay, I'm sorry. There's too much noise in here. Can you repeat the question? I can't.
All right. So, even if we're undecided and we come Thursday for the first portion of the written test,
Yeah.
and we decide after seeing the first portion of the written test to switch and do the oral test.
Okay. I think the best I can do for that is I can let you go ahead and see it. But like once you've actually like really started taking it, then your decision really should be made at that point. Like before. Okay. Like I'll let you see it. But as far as like actually taking it, once you start really taking it, then you're roped in.
Okay.
Yeah.
So we can take a glance at it and make a decision there and there.
Yeah, that is your last possible moment to decide.
Okay, and then the oral exam. Are you basically just going to be standing in front of the class asking questions?
So that's done on an individual basis. So if you want to go that route, then we'll figure something out, like, because depending on how many people are taking it, and when, I may be able to come down there, or we can, or if we're able to use this room, we can do it that way. We'll figure it out technologically.
So it'll be one-on-one, you asking me questions and I have to answer verbally.
That's right.
Okay. That was my question. I didn't know if you were going to be standing in front of the classroom asking questions verbally and us writing them.
Oh no, this is one-on-one thing.
Okay. All right.
Well,
And you said the practice test is more like for the written test. There's not really a practice oral test.
that's right. Your best practice for the oral and also lightning round are the concept check questions.
Okay. So like the quiz is online.
Right.
Okay. That's all I have.
Okay.
Thanks.
Yep.
Another question? Yeah. I don't know.
No, I was just gonna say I do want to do it oral.
You do. Okay.
And I was thinking maybe either Monday or Tuesday because
Okay. I have someone scheduled for Monday afternoon, but we haven't set a
no, it
specific
would just
time.
need to be like 11 or 11:30 probably.
On Monday.
Yeah, or I could do Tuesday just about any time.
Okay.
Tuesday.
I'll keep it in mind as more people talk to me.
Okay, because I'm supposed to be in the math zone Tuesday at 1:15, but I can always change
Yeah.
that. So
Okay.
that's the only thing I have to do.
Oh, whoops! I need to